Hello everyone and welcome to lesson 4-5. Today we're going to talk about tessellations and compositions of transformations. First of all, a tessellation really is a pattern or tiling of shapes that fill a plane. So a lot of our classic patterns that we're used to seeing in fashion or design are actually tessellations. I've recreated the houndstooth pattern here, and if you look, houndstooth is simply repeating this basic shape from up here and tiling it with itself to fill a plane. The definition of a tessellation is a repeating pattern of figures with no gaps and no overlaps. Now, within the big family of tessellations, we have some specific types of tessellations that we're interested in as well. The first are regular tessellations. And a regular tessellation is a tessellation composed entirely of one kind of regular polygon. Now, what makes a regular polygon? A regular polygon is a polygon where all of the sides are congruent and all of the angles are congruent. So if I'm looking at the family of quadrilaterals, the regular quadrilateral is a square because all of its sides are congruent and all of its angles are 90 degrees. So let's take a look at some regular tessellations. The first tessellation we're going to look at is the equilateral triangle tessellation. And equilateral triangles have 180 degrees, which means each angle in an equilateral triangle must have 60 degrees. Well, if you look, those completely fill the plane really well, and one of the reasons why they do so is because as we put all of these corners together, the degrees in the triangles are going to meet and form a 360 degree angle. So if you look, 60 goes into 360 6 times, so we are able to fit 6 triangles together at one vertice. Now let's look at the four-sided tessellation, the square. Now, as we all know, squares have 90-degree angles, which is really nice, and they also tile perfectly. And the reason they tile perfectly is because 90 goes into 360 4 times. So it fits together perfectly. Now let's look at an example that doesn't work. Now let's look at another example, the pentagon. Our pentagon has 108 degrees at each vertex. Now, I know y'all haven't learned about why that happens yet, but we will in a later unit. Just know for now that it has 108 degrees at each vertex. So, if I look at this example here where I try to fit 3 of them together, let me see how many degrees will be meeting at that one vertex. 3 times 8 is 24. I get 324 degrees. Well, clearly that's not 360, which explains why we have a gap here. So it's not a tessellation. Well, let's look and see what happens when I try to put 4 of them together. 108 times 4, I get 432 degrees. Well, again, that is much bigger than 360. And if you look here, we have an overlap. So we cannot tessellate a pentagon in the plane. Now let's take a look at the hexagon. Each hexagon has a vertex with 120 degrees. Again, you'll learn about why that is in a later unit. But if each vertex is 120 degrees, I'm looking at one vertex. It looks like 3 of these shapes are meeting. So if I do 120 times 3, I get 360 degrees. That's great. So therefore, the hexagon can tessellate in the plane. Can you find any more regular tessellations? Tell me why or why not. We'll discuss it in class. We have another kind of tessellation, and that's a semi-regular tessellation. And a semi-regular tessellation is a tessellation composed of two or more regular polygons such that any vertex has the same polygons in the same order. So what does that mean? I'm going to look at one vertex. Look at that one. And I'm going to look and see at what order the shapes meet. I'm going to label them by their number of sides. This guy is 6, squares have 4, triangles have 3, squares have 4. Great. Now I'm going to pick another random vertex that doesn't look like it's in the same position as my other one. I'm going to go here. Same order. 6, 3, or 6, 4, 3, 4. And let's do another one. It's the same order again. Therefore, this is a semi-regular tessellation. We can also have tessellations that are not made up of any regular polygons as well. The houndstooth tessellation from the first page is an example of a tessellation that is not composed of regular polygons. Now let's talk about composition of transformations. Any translation or rotation could instead be achieved by performing two reflections. So, for example, if I were to reflect a shape twice over parallel lines, that has the same effect, if you look, as a translation. And furthermore, if I have a composition of transformations that reflect over two perpendicular lines, that has the same effect as a rotation. Because if I look at this point here, he ends up over here, he rotates 180 degrees. We have one special kind of composition of transformations, and that's called a glide reflection. And a glide reflection is a composition of a translation and a reflection where the line of reflection is parallel to the direction of the translation. So looking here, first we translate it this way, which this is my translation vector right here. And then we rotated this shape across the line, reflected this shape across the line to produce that shape. If you are going to do two or more transformations on an object where you don't revert back to the original for the second transformation, then you're making a composition of transformations. So anyway, that's all the notes for today. Thank you all very much and have a great day.